Welcome to Chapter 4, describing the relation between two variables. Up until this point, we've just been working with one variable. And then just to kind of throw in a quick vocabulary term, when we're working with one variable, we get univariate data. And when we work with two variables, which we're doing in Chapter 4, now it's called bivariate data. All right, so again, this is Chapter 4, and basically everything we were doing before in Chapter 3 was that one variable data, the univariate. Okay, so we've already had some of these definitions, so this part's kind of a quick review. We know the response variable is the variable who can be explained by the value of the explanatory variable. We can also call that a predictor variable. That's a new term for us. And the easiest way to see how an explanatory variable affects the response variable is with a scatter diagram. So we're going to look at a visual display of the data. All right, so definition of a scatter diagram. It's a graph that shows the relationships between two quantitative variables, still working with quantitative, measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is the horizontal axis and the response variable is the vertical axis. So let's just look at a quick visual of that. So if this was our scatter diagram, the x-axis is your explanatory variable. And the vertical axis is the response variable. All right, so we would have a particular value of the explanatory variable. Let's say we applied, we'll just make it generic right now, that value to an individual, and in response, we had a value of our variable like this, right? And so that would create this scattered diagram. We'd have all these points, right? All right, so for instance, let's look at coffee and sleep. Let's say the explanatory variable in our quick example is amount of coffee, so we can just call it number of cups of coffee. And then the response would be maybe something like hours of sleep. And this would be per individual. So let's say we had some sort of sample. I'll do these little dots in blue, just this really quick example. And let's say someone had 5 cups of coffee. And then that night, they were up all night, so they didn't get a lot of sleep. So let's say they got 6 hours of sleep. All right, and so then we would plot that blue point. Let's say another person, I'll do this one in green, had 1 cup of coffee. And so they slept very well and they got the appropriate amount of sleep, which specialists say is 8 hours. And so then there would be that dot. And each dot represents an individual, and we would have however many individuals are in our sample, that's how many dots we would have. All right, so there's the basics of the scatter diagram. Let's look at an actual example. Okay, so this example, the data shown right here are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. Draw a scattered diagram of the data. I would say, reading this, I would say that whether the time it takes to dry drill of distance of 5 feet in rock, I would say it does increase with depth, because we know as we dig deeper into the earth, the dirt gets more compact, and so it's harder to drill, right? Think about when you're at the beach and you start shoveling, the sand on top is really soft and you can go quickly, and as you keep digging on the beach, the sand gets more and more compressed. It takes a longer time to dig the deeper you go. All right, so that's what happened here. Let's look at our data set. So what this is saying, this is the value of our explanatory variable. This is the depth at which drilling begins. So for instance, if we start drilling at 50 feet, it would take 5.99 seconds to drill 5 feet, versus if we began drilling at 175 feet, it would take 7.62 seconds to drill 5 feet. All right, so let's start with our scattered diagram. So what we're going to do is we are going to essentially graph all of these points. All right, so this happened, or this was measured, these 2 points correspond, so it's going to form an XY pair. And we're going to go all the way down to the very last value and do that too. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to graph. And again, if you just want to include this in your notes, the first column is the explanatory variable. So that's going to be on your horizontal axis. And your second column is the response variable. So where the depth we're beginning to drill explains how long it takes to drill. Okay, so we can label our axis. This is going to be depth at which the drilling begins. Notice it's the exact title of the column we're drawing our values from. Units are important, so we'll let the reader know it's in feet. It's all about communicating what's going on. All right, and then we can say this is time to drill 5 feet. And it's in minutes. Okay. So let's also, we have the seconds already here, or the minutes already here. Let's start doing our depth. I'm going to go in increments of 25. So 25, 50, 75, 100, 125, 150, 175, 200. All right, and we can just determine that. Remember, we can look at the depth at which we began, and we can just plan accordingly. It has to range from 35 to 190. All right, and our first ordered pair is 35 and 5.8, 8, maybe something like that. Whoops. And we can just do the best we can. And then 50 and 5.99, a little bit bigger. 75 and 6.74. $95 and 6.1, a little bit smaller. 120 and 7.47. 130 and 6.93. 145 and 6.42. 155 and 7.97. 160 and 7.92. So we could see that the tendency is increasing. 175, 7.62. 185, 6.89. And 190 and 7.9. All right. So there you go. So some things we can use to describe this. We do see, I mean, granted, we have points that are some going up and then down, up and down, up and down, up and down. But I would say in general, this is increasing. It's not strictly increasing, but if we were to maybe kind of visualize a line going through this, that line would be an increasing line. So some words to describe it is we could say that this is increasing. And let's learn some more vocabulary words of how else we could describe this. And we'll go over the calculator instructions in the next video. Okay, so like I said, if we wanted to draw a line through this, it would be an increasing line. And so we could say that this is a linear relationship. So we're going to talk about the three different kinds of relationships between the variables. We're going to focus mainly in this section on linear relationships, or rather I should say in this chapter, linear relationships. It could be a positive linear relationship or negative. Okay, so if we were to draw a scattered diagram, an example of linear relationships, well, when the explanatory variable increases, the response variable also increases. So this is a linear relationship, and again, we can just kind of envision this line going through. Or a negative linear relationship. So as the explanatory variable increases, the response decreases. And again, we can just kind of imagine this red line. That's not part of the diagram, but we can kind of visualize this. All right, we could have a nonlinear relationship between our explanatory and response variables. So go back to your algebra class and think about graphs that aren't lines. And those are your nonlinear relationships. So maybe something like a parabola. All right, so maybe the scattered diagram looks like this. Maybe our scattered diagram is like some sort of cubic. Or excuse me, no, cubic, yeah. So something like this, so increase, decrease, and increase again. These are all nonlinear relationships. They cannot be modeled by a line. And then finally, the other type of relationship between the variables that we might see is just no relation. So this is, there's no pattern of any sort. So in other words, all of our dots are just kind of all over the place. So as one increases, as the explanatory variable increases or decreases, it doesn't mean that the response variable does the same thing or does the opposite. Okay, so like I said, we're going to be focusing on the linear relationship. And we're going to focus on positive or negative. And we're going to call that association. Okay, so the association is for linear relationships. And we can have a positive association or a negative association. All right, so let's break that down. We'll draw two. So we'll look at positively associated and negatively associated. Okay, so positively associated, we kind of already touched on this, or I said it briefly, but I'll use a highlighter. For positively associated bivariate data, as the explanatory variable increases, the response variable also increases. So you're going to see, you're going to see if this is a value of your explanatory, this could be a value of your response. And then as it increases, the response variable also increases. So you're going to get values in here. And then likewise, as the explanatory variable decreases, your response variable also decreases. So if you had a value right here for the explanatory, your response variable would be right there. And then as it decreases, the response variable also decreases. So we're going to get values in here. All right, so that's our positively associated. Negatively associated does the opposite. As our explanatory variable increases, the response variable decreases. And we'll actually write it down here. The response variable decreases. All right, so again, there's an explanatory value, there's a response. And then as the explanatory decreases, the response is going to, as the explanatory increases, the response will decrease. So we'll have values there. So we're going to get values all in here for negative association. And then likewise, as explanatory decreases, our response increases. So if we have a value right here for our explanatory variable, as the explanatory variable decreases, the response variable increases. We're going to get a value right there. And so this is our scattered diagram. Okay, so some examples of positively associated. We can think of this type of model when we're talking about height versus weight. As our height increases, the weight increases. As our height decreases, the weight also decreases. Sometimes another example could be study time versus GPA. The longer you study, the higher your grade point average. We can even do silly ones, like the amount of cookies you have versus the number of ounces of milk you need, if that's your thing. The more cookies you have, the more milk you need. All right, negative association. Let's see if we can think of that. We looked at the example on the first page, hours of sleep versus ounces of coffee. That had a negative association. The less sleep we have, the more coffee we need. And vice versa, depending on the study. The more coffee we drink, the less we sleep. And there you go. You can even, these ones are always a little bit harder to think of, but let's say the elevation. So if you go up the mountain, you're getting higher, so the elevation is increasing, but the air pressure is decreasing. That's why your ears pop. All right, so that's a negative association. Okay, so if we go to our first example of our scattered diagram, we said it was increasing. We can also say it has a positive association, or it's a positive linear relationship. Both of those are appropriate. So we could say positive linear association. Okay. Let's scroll on down back to our association. We have our technical definitions of positively and negatively associated. I forgot, I didn't spell that right. Let's fix it. Positively. Sorry about that. They do it in terms of above and below average. So if we're positively associated, it says when above average values of one variable are associated with above average values of the other variable, and vice versa. So if we were to come up to our positively associated, and we'll do, let's say the average value is right in the middle. So that's for our explanatory, and then this could be the average value of your response. Okay, so notice that this quadrant right here, it's above average for the explanatory variable, and it's above average for the response variable. And down here too, this one is below average for explanatory and below average for response. Okay, so that's where that technical definition is coming from, or what they're talking about. And likewise over here for your negatively associated, if those were your averages, here your above average for the explanatory has below average for the response. All right, and vice versa. Okay. So let's carry on. So we had our scatter diagram. Again, let's just write it twice so everything is neatly organized. How would you describe the scatter diagram from the previous example? We already said positive linear. We can also say positively associated. Because we do have that line. All right, and then it says, how are the digging depth and time to dig 5 feet associated? Again, positively associated. And then here's this tricky part. Is this open to interpretation? I would say yes, because if we went back to our graph, some might say, all the way up, some might say that it varies too much. At first, yes, there's a positive association, but then it was going a little bit down and up, down and up. So maybe they're saying that looks like a nonlinear relationship to me. Whereas someone else might come in and say, no way, this is a line and it's fine. Also, and we saw this when we were doing our misrepresentation of data, if we change this viewing window and maybe limit it to this part, we're going to get a completely different picture too, because we know that we can change a visual display just by changing the window. So the point is, just looking at a scattered diagram and asking if it has an association, positive or negative, it's open to interpretation. So is this open to interpretation? Yes, because we're just answering this question based on a visual understanding. So because it's opinion based, it's open to interpretation. So we need a better way. We need a numerical way to determine if there's any type of association. So we need a better way to measure the relationship. So again, measure means numerical. Okay, so what we do is we look at something called the correlation coefficient. And the correlation coefficient measures the strength and direction of linear relationships. So the correlation coefficient measures the strength and direction of linear relationships. Okay, so the linear correlation coefficient, we use small little letter r. It measures the strength and direction between two quantitative variables. Rho, This Greek letter right here is for population correlation coefficients, but we don't use that in this class. We're just going to focus on R for samples. All right, and then this is our formula. This is our formula. And it looks crazy, so we're going to be dependent on our calculator for sure. But really what this is, if you recall from your previous sections, this is an observation minus the mean divided by the standard deviation. Does that sound familiar? That's a z-score. So we're looking at the product of the z-scores of each observation, or the corresponding explanatory and response variable, and then we take the product. All right, so essentially what's happening is, let's say we have a negative association on our scattered diagram. So that means we have above average and below average values. So if this is a negative association, this would be, let's say, above average. This would be below average. So this would be positive times negative. This whole product would be negative. All right, and so then we're going to be adding up a whole bunch of negative products. And so this whole thing is going to be negative. So if it was a negative association, R is negative. If we had a positive association, this z-score could be positive, this one would be positive. Likewise, if it was a positive association, if this was negative, this would also be negative. And so the whole thing is always going to be positive. Okay, so that's just kind of quickly explaining the formula. You don't really have to know that. It is important to kind of understand where that's coming from. These are all the symbols. X bar we know is the mean, and S stands for the standard deviation of a sample, and N is always the amount in the sample. What we do have to know is how to interpret the linear correlation coefficient. So this is the important stuff. All right, so the very first thing with our R is always between -1 and 1. R is always between -1 and 1. If R is -1, that means that the variables have a perfect negative linear relation. All right, so your scattered diagram would just be a perfect negative line. And then on the flip side, if R equals 1, that's a perfect positive linear relation. So in that case, it would just be the scattered diagram would just be a perfect positive line. And then the closer we are to those endpoints, the stronger evidence of a linear relation. So let's write that out for 4 and 5. All right, so the closer R is to -1, the stronger evidence of a negative association All right, and likewise, the closer R is to +1, the stronger the evidence of a positive association. Okay, so we know what happens as R tends to -1 and +1. And then if R goes towards the middle, so closer and closer to 0, it means no linear relationship. So it could still be a relationship like a quadratic or a cubic relationship, but it's definitely not linear. So if R is close to 0, it just means there's no linear relationship. Okay, and because we use z-scores to calculate the R, since z-scores are unitless, R is unitless. And then because a z-score uses the mean and the standard deviation, mean and standard deviation are not resistant to those extreme values. So R is not resistant. Okay, so we are going to, in the next video, you guys are going to look at the calculator instructions. But before you guys switch over and look at the calculator instructions, I wanted to do a couple of examples, and then we'll come back and do all the calculator stuff at once. Here's some examples of R and their corresponding scattered diagrams. All right, and then we talked about in number 1 and 2 of the properties of R. So when R is 1 and -1, it's a perfect positive linear relation or a perfect negative linear relation. Okay, and then if we get really close to R, or excuse me, really close to 1.9, we still have a pretty strong linear relationship. And as we move farther away from R, it gets a little bit more iffy. Until finally, when we're really close to 0, it's all over the place, right? And then likewise, or again, close to 0, it could also just mean nonlinear too. All right, and then same thing with the negative. If we're close to -1, it's still a fairly strong negative linear, and as we move farther away from -1, it gets a little bit more iffy, but we can still say there's that negative correlation. Okay, so we'll go over this one in our calculator video. Very last one, we can also talk about positive correlation and negative correlation without even looking at our linear correlation coefficient. It was kind of what we were doing with those examples when we first introduced this. So for instance, here we have explanatory and response variables. We're going to think if the variables will have a positive correlation, a negative correlation, or no correlations, and support your opinion too. So this is a good time for you guys to push pause and think about what you're gonna, what kind of correlation each of these variables have, the bivariate data. And then after you're done, push play and we'll go over our answers together. All right, number of cigarettes smoked by a pregnant woman each week and birth weight of her baby. Well, smoking is associated with low birth rate. So as a pregnant woman smokes more and more cigarettes, so as the number of cigarettes go up, the birth weight of her baby might be low, or it's proven to be low. So if one goes up and the other one goes down, that's negative association. Okay. Number 2, years of education and annual salary. We're not going to think of the outliers, right? The entrepreneurs that make, millions of dollars doing, some sort of blog or something, but the general population. And normally what happens is if you have a higher degree, so like bachelor's, master's, doctorate, so that requires more years of education. your salary goes up with that. So if as one increases, the other increases, that's a positive association. All right. And then we have head circumference and IQ. So is a big head, for instance, associated with a high IQ? No. Is a big head associated with a low IQ? No. All right, so in this case, there's no correlation. Thankfully, right? Okay, I have a small head. Finally, number of moviegoers and movie ticket prices. This one's up to interpretation. So just make sure you support it. So I'm thinking of a couple of different answers. If you guys said, some of you might say no correlation. For instance, ticket prices are insane right now, but people still go to the movies, right? So prices could go up. And people would still go to the movies. All right, you might have answered a negative association. So for instance, if the prices were like $100 across the board, so if the prices were increasing, people would eventually stop going. All right, likewise, if we had really cheap tickets, like $1 tickets, probably it would be really crowded and everyone would go. So as the ticket prices go down, people would go up. And then finally, you could even say something like positive. This is more of like a supply and demand type of situation. If people are demanding movies, then the tickets are going to go up, right? So lots of people, it might drive the tickets up. So whatever you answer, remember, just support it. Because that's kind of what statistics is. It's sometimes open to interpretation. Okay, so we skipped some material. We are going to cover that in the next video when we're looking at our calculator.